Now we'll look at a few more complicated examples of determining the sign of Q and W. This is the oxidation of glucose, C6H12O6, into carbon dioxide and water. And this is, you can tell from Chemistry 1201 that this is a standard combustion reaction. It's a fuel plus oxygen producing carbon dioxide and water. And that's going to be a heat-producing reaction, so heat is going to be a product over here. Now, these types of questions where we're dealing with a reaction as our system, that's where it's going to be very important to use the system surrounding diagram. Because unlike the physical processes that we did in the previous video, we can't really come up with a sketch for this type of process without using some kind of representation of the system. So anyways, it's useful to draw these system surrounding diagrams. We have heat as a product over here, which means that heat is being exerted from the reaction. The reaction is producing heat, which means that heat is leaving the reaction and going into the surroundings. That's what it means for heat to be on the product side of the reaction. Heat is leaving the reaction, going into the surroundings. So we know if heat's going from the system to the surroundings, Q has to be negative. Now work is going to be a little more complicated to determine because previously we were talking about how the heat made the system expand or compress, and that's how we figured out the work. But in the case of a reaction like this, the heat is not going to be what's determining how the reaction expands or compresses. What's going to determine that is the quantity of gas produced or consumed. Okay, so on the reactant side of the equation, we have 6 moles of gas per mole of glucose, right? We're only concerned with gases in this scenario because solids and liquids have negligibly small volumes compared to gases. So gases are what are going to really determine the volume of the system and determine whether it's expanding or contracting. So on the reactant side, we have 6 moles of gas, and on the product side, we have 6 moles of carbon dioxide plus 6 moles of water gives us 12 total moles of gas. So what this means is that as a result of this combustion reaction between glucose and oxygen, we used 6 moles of gas and we produced 12 moles of gas. So we ended up with more moles of gas than what we started with. And we know from Chemistry 1201, from the ideal gas law, that if we add more moles of gas to a container, we increase the volume. In fact, it's directly proportional. So if we double the moles of gas, as we are in this case, we're going to double the volume of that gas. So the volume is certainly increasing as a result of this reaction. And if the volume of the system is increasing, that means it has to push against the surroundings. So the system is doing work on the surroundings by expanding, by producing more moles of gas. So work is going to be negative because the system is doing work on the surroundings. So this is an example of where both Q and W can both be negative. And of course, there are examples where both Q and W could both be positive. And we saw in the last video that there are plenty of examples where they can be opposite in sign. So this tells us that Q and W aren't really necessarily connected to each other. They can take on any sign relative to the other one. All right, so let's try the next one. Again, I want you to pause the video here and try to work this one on your own, and then resume the video and I'll go through the solution. Okay, so we're going to do the same thing. We're going to identify where the heat is in this reaction, and in this case, the heat is on the reactant side, right? Remember, the left side of the yield arrow is the reactants, and the right side is the products. So in this case, heat is on the reactant side. What that means is that in order for this reaction to occur, we have to put heat in to the system. Heat has to enter the system before the reaction can happen. Whereas in the previous example, heat was on the product side, which means that heat was released from the system. In this case, heat's on the reactant side, so it has to be put into the system. So from that, we can tell that heat is entering the system, so Q must be positive. Now we're going to do the same thing we did last time with the moles of gas. We're going to say on the reactant side, we have 1 mole of gas. Remember, there's an implied 1 right here, even though nothing's written. And on the product side, we have 1 plus 2 makes 3 moles of gas. So again, our moles of gas is increasing, which means that our volume is increasing, which means that the system is doing work on the surroundings so that it can expand, and W is negative. All right, we have one more example. Again, pause the video, try it on your own, and then hit resume. All right. Now, first thing we're going to do, just like in the previous two examples, is identify where the heat is, and it's on the product side. So I hope by now you can see where this is going. Heat is on the product side. That means the reaction is releasing heat to the surroundings. So heat is going from the system to the surroundings, which makes Q negative. We're going to do the same thing we did in the previous two examples with the moles of gas. So we identify every place where there is a gas, and we add up the moles on both sides. So on the reactant side, we have 1 mole of carbon dioxide and 1 mole of water, gives us 2 total moles of gas. And on the product side, we have 1 mole of carbon dioxide. I'm sorry, carbon monoxide was on the reactant side, not carbon dioxide. On the product side, we have 1 mole of carbon dioxide and 1 mole of hydrogen gas, which gives us 2 moles of gas as well. Now we run into a problem here because what we were doing before was identifying which side of the reaction had the greater moles of gas so we can determine how the volume was changing. But in this case, both sides of the reaction have equal moles of gas. So what does that tell us about the volume? It tells us that there is no volume change. The volume the volume before the reaction occurred and the volume after the reaction occurred is exactly the same. So there's no change in volume. If there's no change in volume, then the system is neither expanding nor contracting. It is staying exactly the same. And if it's staying exactly the same, that means that there is no work. Work is 0 in this case. It's not positive or negative. There is no work. So the only value we can assign a sign to here is Q, which is negative, and the work is 0 because the moles of gas is equal on both sides. Therefore, the volume is not changing.